just want to do a quick review of what we did yesterday. So yesterday, when we looked at this section here, trying to figure out some information about weak acids, talked about the strength, concentration, and we said that we said that the questions that we look at kind of fall into two categories, and maybe you came across it yesterday, that the two categories aren't necessarily like strict categories here. But for the most part, we break this down into two categories. You're either calculating Ka from some sort of concentration, or you're going to use Ka to figure out the concentration of hydronium of a weak acid. And that's what we're going to do today. But first, I want to just do a quick review of the question number 1 here. So we did do this this question, which you guys were supposed to try yesterday. So you guys decided to jump right into the homework and then talk for a majority of the class. But whatever. Let's just go through this one. So the pH of a 0.400 mole per liter solution of sulfurous acid is measured to be 1.17. Calculate the Ka for sulfurous acid from this evidence. So sulfurous acid is H2SO3. I'd be taking that, I would be putting it in water. I should put aqueous here. Water as a liquid. It's a weak acid, so I have those equilibrium arrows, and then what's happening is one of the hydrogen is breaking off from the sulfurous acid and attaching to the water to produce a hydronium ion and a hydrogen sulfide, ion, which is also aqueous. They are asking me what the Ka of this is. So, to figure out Ka, if we remember from yesterday, you take the concentration of the products. So in this case, you'll take the concentration of the hydronium ions and the concentration of the hydrogen sulfide ion over the concentration of the acid, H2SO3. Now, if I take the information from the question that they gave me, the only thing I know for sure right now is the concentration of the acid, because that's the original concentration of the sulfurous acid is 0.400, so this would be 0.400 moles per liter. And I don't know the concentration of the hydronium ion or the hydrogen sulfide ion, so how can I figure that out? Right, I can use this 10 to the negative pH, so I would go 10 to the negative 1.17, which gives me a pretty high, concentration, 0.068 moles per liter. That's the concentration of the hydronium ion. And then we use an ice table to figure out the rest of the information. So 1, 2, 3, 4. So this is the initial, the change, and the equilibrium of the original acid, sulfurous acid, the ion, and hydronium. So the original concentrations of the products is not there, and the initial concentration of sulfurous acid is 0.400. We just figured out by using the pH, figuring out the pH at the concentration of these hydronium ion would be 0.068 moles per liter. And to figure out the rest of these, I would just do the mole ratio. So 0.068, it's always pretty much a 1-to-1 here. And this would be 0.068. So this would be adding, and subtracting. 0.068. Remember, we're always using the equilibrium concentrations in my Ka formula. So I need to figure...
Why did you put your 0.04 over the previously your Ka?
Oh, yes, sorry, I guess I was making... Sorry, yeah, I guess I was making the assumption that acid didn't have any effect on it. So that's my fault. Remember we said yesterday, if we compare this number and we divide them, and they are greater than 1,000, if I do that, 0.068, which I don't think that will be, we could not include that in my calculation, but those two are significantly close, so I would go 0.068, and I only get like 5 when I divide them, so 0.332. So then I take all those numbers and I can put them into my Ka formula. Both of the reactants are in the exact same concentration, so I'll just go 0.0068 and I will square that over the 0.332. Yeah, there's only one, thank you. And so 10 to the negative. Trying to keep my significant digits in here. Just take that answer, square it, and divide it by 0.332. Gives me 1.4 times 10 to the negative 2. And remember we said yesterday, Ka concentrations, or Kas can actually have a unit, unlike an equilibrium value for Kc. And Ka values are always written to 2 significant digits. Okay, so we're going to look at the second type of question then here today, which is predicting the concentration. So we're kind of like going to be working backwards here, but there are some things that we're going to note here that we kind of skip over. So predict the hydronium ion concentration and pH, so that means I'm going to figure out my hydronium concentration and then figure out the pH, right, using the negative log of the hydronium ion concentration. And then they tell me the concentration of methanoic acid is 0.200 moles per liter. So methanoic acid is HCOOH aqueous. It would be reacting with water as a liquid. It's a weak acid, so double equilibrium arrows. One of these hydrogens is leaving the acid and attaching onto the water, which is in this case the base because it accepts that proton. And so this would be HCOO negative aqueous ion and the hydronium ion. Okay, I'm gonna jump, I guess, into the ice tape. So, like, if I look at this, I should maybe be able to figure out that I can use Ka is equal to the hydronium ion concentration plus the concentration of that ion all over the initial concentration. Whatever that concentration is at equilibrium. Right now, I don't have any information to put in and help me solve anything in there, so I'm going to go to an ice table. So, initial... Trying to leave a bunch of space for myself here. I got a lot of stuff to write down. So make sure you give some room. So initial, change, and the equilibrium. The only piece of information we're given here is that the original concentration of methanoic acid is 0.200. They don't give me the pH, they don't give me the hydronium ion concentration. So, because they don't give me either of these, like these would always be 0. But they don't give me that, so I don't know how much that it's changed by, so we just put a X here. These are increasing by some amount, we don't know how much that amount is, and because everything is in a 1-to-1 ratio, we're just putting X there. That means that the concentration of methanoic acid would be decreasing by some unknown amount. And so if I subtract all those rows, this is an X, or this is a 0.200 minus X. So if I take all of that information and I put it into this formula right here, the hydronium ion concentration is X, the ion there is also X, so I'm just going to put that as X squared, over 0.200 minus X, equals Ka. Now, I can find the value of Ka by going to this relative strengths of acids and bases table, so if you want to grab that out, you can kind of look at it here. So I'm looking for methanoic acid. Methanoic or formic acid is like 3rd or 4th up from the middle of the page. So if I look at that, it tells me my Ka value for that acid, assuming SATP conditions, right, for formic or methanoic acid, that is 1.8 times 10 to the negative 4. That's my Ka value for that. Okay, so if I was to try and solve this right now, like I'd have to cross multiply, and then I would end up with a trinomial that I would have to solve using the quadratic formula. Most of the time, however, we don't have to use the quadratic formula. They give us a shortcut. And so my shortcut, what I need to do, where am I going to write this that they can see it? I'll just write it here and then I'll erase it. So, how did I word this? If I can avoid using the quadratic formula, that's what I want to do. In order to see if I can avoid it, what we do is we take the initial concentration, and you're going to divide it by your Ka value. Similar to what we did before, if we do that and it is 1,000 times greater, can you read that, Yellow? Okay. If it's 1,000 times greater, you assume the equilibrium concentration is the same as the initial. The equilibrium equals the initial const. So I would do a quick test here just to make sure that that is the case. So I would take my initial concentration, which is 0.200, and I'm going to divide that by my Ka, which is 1.8 times 10 to the negative 4. If I do that, I end up with 1,111. So because that is greater than 1,000, I can go and I can skip to the shortcut. This is the HA initial, so therefore the HA initial equals the HA equilibrium. So you can either look at this one of two ways. If you get to this, say, okay, it's greater than 1,000, that means that really what I can do is I can ignore this x here, and I can just go ahead and solve it. Or we have this formula that we can remember, which is over here, that the hydronium ion concentration is equal to the square root of the Ka times the HA. Squaring and square rooting it, so I don't need that square there. That's not right. First square root, we get rid of that. Alright, so really mathematically, that is what I would do. And so whether you memorize that or you rearrange this, it will get you to the same place. That's just the shortcut. Because really what I would do is I would cross multiply here, right, which is what gives me the Ka times the HA. I'm cross multiplying, and then I would have x equals that, and then I would have to square root it. So really that's just what I'm doing is making the formula for the shortcut there. And then I just put my information into here, so I'm just going to continue. Ooh, what is that? That's a highlighter apparently. Alright, so the hydronium ion concentration is equal to the square root of the Ka, which in this case is 1.8 times 10 to the negative 4, times by the Ha, which was 0.2. And so if I put that on my calculator, the hydronium ion concentration is equal to, this question has 3 sig digs, so it would be 0.00600 moles per liter. Sorry, HA is the concentration. This is the, HA just means the weak acid. And it's just, yeah, the initial concentration. Because that is from here, right? The initial concentration equals the equilibrium concentration because it's greater than 1,000. The question's also asking me to figure out the pH. So to figure out the pH, it's the negative log of that concentration, 0.006. And so the pH would equal 2.22003 sig digs.
And that should be 1.8 times 10 to the negative 4?
1.8 times 10 to the negative 4.
Or that's brackets?
Where?
Never mind.
Yes, brackets, sorry. Sorry, I know there's a lot going on there. Once you kind of are able to identify the difference between these questions, I find that I don't always need to create an ice table. If I can recognize that I'm automatically just going to be jumping to this, because if I check my two numbers and this is happening, I can just jump to here and I don't need my ice table for that. If you can eventually recognize that that's the type of question that you're dealing with. So if you're done that one, you want to start working through the next one. We'll finish this right. You can try that. So see how far you can get. Take a minute or two. See what you can do there. Okay, so second example, pretty much the exact same process. Predict the hydronium ion and the pH for a 0.5 mole per liter solution of of hydrocyanic acid. So if you look on your chart, hydrocyanic acid is HCN. I'd be reacting that with water, liquid, aqueous. So weak acid, we'll be producing a cyanide ion and hydronium. And again, if I look at this, like I'm trying to figure out that hydronium ion concentration. So if you can recognize that as soon as I'm figuring out that hydronium ion concentration, I'm either going to have to use the quadratic formula or the other formula, which looks like this, Ka times Ha. You really don't even need to use an ice table, because if I use an ice table, it's not really getting me anywhere for this. HCN, Cn negative, and hydronium ion concentration. I know the original concentration is 0.5, and I pretty much don't know anything else here, right? This is plus x, minus x, 0.5 minus x, x, right? And so all I'm doing is taking a whole bunch of unknowns and putting them into my Ka formula. So what you should have done here is take that 0.500 and divide it by the Ka for hydrocyanic acid. And so if you go to your chart, HCN is pretty weak acid. It's down towards the bottom here. So the Ka value is 6.2 times 10 to the negative 10. And just looking at that, I already know that that's going to be way bigger than 1,000, right? That's a really, really small number to go into 0.5. So it's probably like a few million. So that means I can automatically just jump into this formula. Does that make sense? Everybody understand that? Yeah. Okay. So figure out the hydronium ion concentration. The Ka value we just got from the chart was 6.2 times 10 to the negative 10. And I always just make sure I put brackets around my calculator when I put that in. Times by the original concentration of the acid, which equals the equilibrium concentration of the acid because of this that I just did. So I times that by 0.5, And so the hydronium ion concentration is 1.76 times 10 to the negative 5 moles per liter. 3 sig digs, so that would be my correct answer for that part. And then to figure out my my pH, it's the negative log of that, 1.76 times 10 to the negative 5. That's 5, right? And so your pH, written with 3 significant digits, is 4.754. Yeah. Yeah, so this is 3 in total, right? Because leading zeros aren't significant. So this has 3 in total, and then this is the 3 significant. Yeah. And I mean, like, we're not really doing written response. Like, if I give you a question on the test, then it would matter. But most of the time, if you're looking on the diploma, pretty much all the ones I've seen, you kind of just fill it in, but don't always, I guess, judge on that. So. Okay, so if you ever come into a question where a Ka value, they're not looking for a Ka value in particular, then you're going to be getting the Ka value from the table. Not all the questions that we're going to come across follow these exact 2 categories where you're either figuring out Ka or you're figuring out concentration of hydronium. Sometimes they change it up, and I think there's 1 or 2 questions in that homework 9 that do that. So make sure you're kind of, if you don't know Ka and they've not asked you to find it from your table. Okay, so you guys are going to go through, finish up homework 9, what you didn't do yesterday. Homework 9, and we're talking about the first homework 9, not the second homework 9, because I don't know how to count. And so we went up to 6 yesterday.
Yeah.
So you can either do 7 and 8. 7, 8, 9, and 10 or 11. 7, 8, 9, and 10 or 11 for the first homework 9. Again, all those answers are online.
Isn't 7 and